In this video, we're going to talk about how to use generating functions to solve a nonlinear recurrence. Let P of n denote the number of regions the plane is divided into by n non-parallel lines, where no more than two lines intersect at a point. At some point, you might have seen that this satisfies the recurrence P of 0 equals 1, and P of n equals P of n minus 1 plus n for n is greater than or equal to 1. You can find this just by playing around with the geometry of the situation. And you might have also seen a formula for the explicit value of Pn, but we don't really know where that formula comes from. What we're going to do is we're going to use generating functions to show where that comes from. So let's start by defining our generating function P of x equals the sum from n equals 0 to infinity of P of n x to the n. Since my recurrence doesn't really start until the second step, let's go ahead and pull out the first term. And then start our sum at 1, go from n equals 1 to infinity. And now that we're starting at 1, I can go ahead and rewrite this using my recurrence. So this is going to be 1 plus the sum from n equals 1 to infinity of Pn minus 1 plus n x to the n. And we can go ahead and split those up into two pieces. Okay. Now that we've split that up into two pieces, let's go ahead and dissect what each of those actually are. So when I look at this sum n equals 1 to infinity of P of n minus 1 x to the n, I can re-index this by letting n start at 0. If n starts at 0, then, well, let's think. In this case, we wanted the first term to have a p0 up front. So if n starts at 0, that's going to become the sum from n equals 0 to infinity. This will just be Pn instead of Pn minus 1. But I need the first term to have an exponent of 1. So this is actually going to be x to the power of n plus 1. Just by re-indexing that n. You can think of changing n minus 1 to n prime if you want to do a little bit of algebra to actually solve that out. But what we notice is that I can also factor out an x here. And then since this is just the generating function, this is going to be equal to x times p of x. So I now know a fancy way of rewriting this. I also have a fancy way of rewriting our other sum. To do that, I'm going to recall that 1 over 1 minus x is equal to the sum from n equals 0 to infinity of 1x to the n. And one thing I know is that if I want to multiply by n, I take the derivative and then multiply by x. So let's go ahead and do that. If I take the derivative, on the left side, what I'll end up with is 1 over 1 minus x squared. And on the right side, what I'll end up with is n equals 0 to infinity. I'll end up with, actually, I should go ahead and make this a 1, because the first term is going to disappear. The first term disappears, and then everything after that, we're going to end up with n times x to the n minus 1. Which, if I now multiply that by x, on the left-hand side, I'll get 1 over 1 minus, or x over 1 minus x squared. And on the right-hand side, basically that'll just fix my index over here. And I get the sum from n equals 1 to infinity of nx to the n, which, even though that's exactly what we want, it's worth noting that this is also the sum from n equals 0 to infinity of nx to the n. Because, of course, when n equals 0, we'll get 0 for the first term. So we have that. So now we know how to rewrite both of these. We've essentially concluded that p of x equals 1 plus this term actually equals x times p of x. And this second term equals x over 1 minus x squared. It's worth noting that both of these are very common techniques that will come up when we're working with generating functions. So you should feel comfortable, A, turning something like p of n minus 1 x to the n, just recognizing that's x times p of x. And also you should be comfortable with this taking the derivative and multiplying by x business over here. So we have those two things. Now I want to go ahead and solve for my recurrence. So let's go ahead and solve for p of x. Let's get the p of x's to one side. I'll have p of x minus p of x times x equals 1 plus x over 1 minus x squared. I can go ahead and factor out a p of x on the left-hand side. That'll be p of x times 1 minus x equals 1 plus x times 1 minus x squared. And then I'll just multiply both sides by 1 over 1 minus x to get p of x equals 1 over 1 minus x plus x over 1 minus x cubed. First one, I know the generating function for that. We've actually already written it on the screen. That's going to equal the sum of 1 times x to the n. So that we know. This one's a little harder. But if you've done your homework, well, kind of, tongue-in-cheek there. If you've done your homework, you might actually know that 1 over 1 minus x cubed should potentially equal the sum from n equals 0 to infinity of n plus 2 choose n. Or n plus 2 choose 2. Either of those are equivalent. I'll go ahead and use n plus 2 choose 2 here just for the sake of simplicity. X to the n. So that means that x over 1 minus x cubed should equal the sum from n equals 0 to infinity of n plus 2 choose 2 x to the n plus 1, which you can go ahead and re-index to the sum of n equals 0. Actually, no, that would be n equals 1 to infinity of n plus 1 choose 2 x to the n. And you can verify that both of those first terms will look the same. And let's go ahead and just rewrite that to make life a little easier. This will end up being n equals 1 to infinity of n times n plus 1 over 2. That's what n plus 1 choose 2 will look like, x to the n. And at this point, kind of like what we saw earlier here, we noticed that I was able to start my sum at 0 instead of 1 because the first term is going to be 0 if I plug in 0 for n. I can do that exact same thing here. So since the first term is going to be 0 anyways, I might as well just start my sum at 0. Oh, we'll do one other thing before we do this. Let's go ahead and FOIL that out to get n squared plus n over 2 x to the n. And we're almost there. We've done most of the hard work. I'm going to scroll down a little bit so that we have a little bit more room. And what you'll notice is that I can combine these into a single sum. I can turn this into 1 plus n squared plus n over 2 times x to the n. And if I find a common denominator and rearrange my terms a little bit, you should be able to see that that equals n squared plus n plus 2 over 2 times x to the n, which means that this is going to be p of n. So we conclude that p of n equals n squared plus n plus 2 over 2, and that's going to be the solution to my nonlinear recurrence. So We had to use a lot of recognition and a lot of little generating functions tricks. We needed to be able to deal with previous terms. We needed to be able to multiply by n. And we also needed to recognize, what do I do when I have a fraction that has a higher power of something like 1 over 1 minus x squared? Or sorry, a higher power of something like 1 minus x in the denominator. We also did a lot of re-indexing and just a lot of generally fun stuff. So with all that, we were able to find an explicit formula for that generating function. So there you go.